research in Philippine Normal University entitled Development of Supplementary Material to Enhance the Graph Interpretation Skills of Students. I am a faculty member of the Basic Education Department and a part-time faculty of College of Education on Arts and Sciences of Colegio de San Juan de Latran, Calamba City, Laguna, Philippines. Kinematics is often the first topic discussed in physics. Most of the ideas in kinematics, such as position, velocity, and acceleration, are incorporated into almost all branches of physics. If there is no solid understanding of kinematics, students would lack the foundation necessary to succeed in the following lessons, as physical concepts become more abstract and complicated. Because of the fundamental nature of kinematics in the whole of physics, any improvement in student understanding of these concepts enhances the possibility of comprehension of physics that the students would encounter throughout the year. On the other hand, physics teachers are always challenged on how to build the best foundation for the students to learn, which would help them cope with the mathematical aspects of studying physics. One of the methods used by physics teachers to answer this challenge is the use of graph. A graph is a diagram showing the relation between two variable quantities. It helps to represent physics formulas, which are abstract forms of the existing relationship between physical quantities. There are so many studies conducted in kinematics graph. They are with Ellis and Turner in 2002, McDermott in 1987, and Bickner in 1994. Most of them concluded that students have difficulties when it comes to kinematics graphs. So these are the difficulties of students when it comes to kinematic graphs that was suggested by Dr. Robert Bickner in 1994 with his study testing student interpretation of kinematics graph. And because of this, Dr. Bickner developed an instrument which he called a standard, actually the standard instrument in measuring kinematics graph, understanding of students in kinematics graph, which he called Test of Understanding Graphs in Kinematics, or the TUGK. It is an instrument designed to disclose student difficulties with position, velocity, and acceleration versus time graphs. According to Bickner in 1994, whether the instruction was exemplary or ordinary, the students were not able to fluently interpret kinematics graphs. Therefore, I believe that the supplementary material should be given to students to increase their level of understanding of kinematics graphs. Statement of the problem. Number one, what is the level of graph interpretation skills of students in kinematics? What are the common difficulties of students in interpreting kinematics graphs? How valid is the developed supplementary material? Is there a significant difference between the pre-test and post-test scores of the control group and the experimental group? Is there a significant difference between the change scores of the control and experimental groups? Since, from the title itself, development of supplementary material, so this is a developmental research, I had first identification of student difficulties in understanding kinematics graphs. So their scores, I used my fourth-year students in physics class to identify the difficulties of students when it comes to kinematics graphs. After which, I developed the supplementary material. Since this is a developmental research and I had my supplementary material, I undergone the 5 phases: planning and organizing, gathering materials and references, writing of the material, content validation and evaluation by experts, and the final revision. And finally, to determine the effectiveness of the supplementary material, I use experimentation. So I administered pre-test and post-test to the students. Of course, the research instrument use, TUGK, I asked permission from Dr. Bickner, and he sent me the latest version in 2010. The items were written for each objective, producing a 26-item multiple-choice type of questions, which has a reliability of 0.78. And then to validate the supplementary material that I prepared, I used Likert type scale to assess the acceptability and validity of the supplementary material. These are the objectives: the item distribution, It is consists of 26 items, so you have different types of graphs, and the objectives of these graphs. So let's say, for example, you have a position time graph, then you're going to determine velocity and the rest. To determine the effectiveness of supplementary material, I use quasi-experimental design, specifically the non-equivalent pre-test, post-test control group design, since randomization process and selecting and assigning samples to the experimental group and control group were not possible because I already chose those groups, the classes that I handled. So that's why it is quasi-experimental. Included in the supplementary material are the objectives, lesson proper, computer simulations using the internet and drills. The module followed the general trend of using desktop publishing layout for ease of reading. In addition, there were inclusions of simulations and computer-based activities so that the supplementary material would be applicable to the needs of the 21st century learners. Presentation analysis to answer the SOPs. What is the level of graph interpretation skill? So as you can see, out of 26, so the students got low. So for the interpretation, the mean score is 4.06 with standard deviation of 1.658, meaning there are 62 out of 78 students are in the low level in interpreting kinematics graph. Second, common difficulties of students in interpreting kinematics graph. So you have the different types of graph with their objectives, and you have the difficulty index. So I already had the summary here for the difficulty indices. And as you can see, a kinematics graph select textual description ranked number 1 as the most difficult type of graph, which has a difficulty index of 0.833 and standard deviation of 0.932. Overall, the test, the students got a difficulty index of 0.778 with standard deviation of 3.590, which is verbally interpreted as difficult. How valid is the supplementary material? I have 4 physics experts who validated the supplementary material. And you have objectives, content and simulations, language and layout, and the overall mean got 4.48, standard deviation of 0.317, which is verbally interpreted as very much acceptable. That's why I used now it to the 2 groups. Is there a significant difference between the result of the pre-test and post-test for the control group? So as you can see, you have the performance profile for control group. So you have the frequency. For control group, I have 25 participants. During the post-test, the mean score is 14.48 there, the post-test. If you're going to compare it to the performance during the pre-test, it is 2.72. So the mean difference is 11.70, so very high. But to further accept or reject the hypothesis, I use ANOVA control group for post-test versus pre-test. So the obtained F is significant for 149 degrees of freedom, which has a critical value of 4.20. In addition, a P level of 0.00 with a verbal interpretation of extremely significant. So for the subject, so 24 to 49 degrees of freedom, the obtained value for subjects of 0.909 is not significant. That does not exceed the critical value, indicating that the characteristics of the respondents did not interact or affect during the conduct of the study. Is there a significant difference? So we had the control group, let's have the experimental group. As you can see, during the post-test, the mean score, so out of 26, the mean score for post-test is 18, while during pre-test, the mean score is 2.70. So as you can see, the mean difference is 15.30. So to further accept or reject the null hypothesis, I use ANOVA. So as you can see, the F value is 379.822 with P level 0.00, which indicates that there is an extremely significant difference between the pre-test and post-test results of the experimental group. Now we are going to see if there is a significant difference between the change scores of the control and experimental groups. I use t-test for independent means to get this. So as you can see, you have the control, the change score is 11.76, mean score pala, mean score, and then experimental group is 15.30 with a mean difference of 3.54 with a t-value of 3.13 and a p-level is 0.001, which indicates that there is a high significant difference between the result of the pretest and between the control and experimental groups. So what are the conclusions? The developed supplementary materials based on the results of the level and difficulties of students on graph interpretation skills and kinematics. According to Bickner in 1994, the students do not fully understand kinematics graph, even if the instruction was exemplary or ordinary. That is, the students were not able to fluently interpret kinematics graphs. Students do not have ample knowledge and understanding the slope and area under a curve or a line in kinematics graph. They use incorrect methods to get correct answers. So they believe that kinematics variables behave identically or very similarly and must therefore be graphed similarly. And see graphs as representing the physical path of motion. In addition, Bickner in 1994 mentioned that students entering introductory physics classes understand the basic construction of graphs, but have difficulty applying those skills to the tasks they encounter in the physics laboratory. The developed supplementary materials proven to have validity as assessed by experts. It can therefore be concluded that the material is effective in supplementing the learning of students in terms of the graphical analysis of motion. With a post-test of control and experimental group, it can be concluded that the test of understanding graphs kinematics developed by Dr. Bickner is comparatively difficult, considering that the total score of the said test is 26. There is a significant difference between the pre-test and post-test scores of the control group. In the same way, there is also a significant difference between the pre-test and post-test scores of the experimental group. As mentioned by Kitao, curriculum, materials, teaching methods, and evaluation should all be designed for learners and their needs. Therefore, in this study, the use of supplementary materials is an effective way in order for the students to overcome difficulties in understanding kinematics graphs. Reyes cited in Cruz 2008, the supplementary material can be great help to a student who encountered a hard time in understanding a particular topic. In addition, Hughes stated that teachers can help students through individualized instruction by giving them additional materials such as activities that contain written exercises. Recommendations. The developed supplementary material must be used after the discussion of graphical analysis of motion in order for the learners to further understand kinematics graphs. There must be coordination between mathematics and physics teachers in the teaching of kinematics graphs, inasmuch as these topics are included in the mathematics subject matter plan. These will help the physics teachers reduce the difficulties of students in understanding slope and area under a line or a curve in a graph. Physics teachers must utilize graphs more frequently in their physics classes to strengthen students' understanding of physics concepts and to enhance their problem-solving capabilities. Conduct a seminar workshop for physics teachers, especially those who do not have specialization in physics that focuses on graphical analysis of motion. Maraming salamat po. Thank you very much.